A bit earlier, you learned how a cluster consists of one or more nodes. This is one of the ways in which Elasticsearch can scale, both in regards to data storage and disk space. If we want to store 1 terabyte of data and we only have a single node with 500 gigabytes of space, that's obviously not going to work. However, if we add an additional node with sufficient capacity, Elasticsearch can then store data on both nodes, meaning that the cluster now has enough storage capacity. But how does that actually work? Elasticsearch does this by using something called sharding. You might have heard of this term in the context of databases, for instance, and the concept is the same, so let's take a look. Sharding is a way to divide an index into separate pieces, where each piece is called a shard. Notice how sharding is done at the index level and not at the cluster or node level. That's because one index might contain 1 billion documents, while another may only contain a few hundred. As you might imagine, this affects how the indices are configured. The main reason for dividing an index into multiple shards is to be able to horizontally scale the data volume. Let me give you a simple example of how sharding works. Suppose that we have 2 nodes, each having 500 gigabytes of storage space available for Elasticsearch. We have a huge index, taking up 600 gigabytes of storage on its own, meaning that the whole index does not fit on either node. Therefore, running the index on a single shard is not an option, because a shard needs to be placed on a single node. Instead, we can divide the index into 2 shards, each requiring 300 gigabytes worth of disk space. Doing this, we can now store a shard on each of the 2 nodes without running out of disk space. We could also have a higher number of shards if we wanted to, such as 4 shards of 150 gigabytes each. We still have space to spare, so we could use that for other indices if we needed to. Just to be clear, a shard may be placed on any node, so if an index has 5 shards, for instance, we don't need to spread these out on 5 different nodes. We could, but we don't have to. Alright, hopefully you understand how sharding makes it possible to scale the amount of documents we can store. Of course, sharding goes hand in hand with increasing the available disk space if necessary, potentially by adding more nodes to the cluster. Each shard is independent, and you can think of a shard as being a fully functional index on its own. That's not 100% accurate, but close enough. Remember how Elasticsearch is built on top of Apache Lucene? Each shard is actually a Lucene index. This means that an Elasticsearch index with 5 shards actually consists of 5 Lucene indices under the hood. While a shard does not have a predefined size in terms of allocated disk space, there is a limit to the number of documents a shard can store, being just over 2 billion documents. As I said a few moments ago, the main reason for sharding an index is to be able to scale its data volume, being the number of documents it can store. By using sharding, you can store billions of documents within a single index, which would usually not be feasible without sharding. Another common use case for sharding an index is to divide an index into smaller chunks that are easier to fit onto nodes. Yet another reason why sharding is useful is that it enables queries to be distributed and parallelized across an index's shards. What this means is that a search query can be run on multiple shards at the same time, increasing the performance and throughput. Remember that the shards may be stored on different nodes, meaning that the hardware on multiple nodes may be utilized. If you're wondering how Elasticsearch searches for data across multiple shards, then don't worry about that for now, as I'll get back to that later in the course when relevant. Let's head over to Kibana, where I've prepared a query, which you have already seen before. Let's go ahead and run it to list the indices within our cluster. Looking at the results, we can see a column named PRI or PRI, being short for primary terms. I haven't told you what a primary shard is yet, but I will in the next lecture. Until then, just think that this column represents the number of shards that a given index has. We can see that each of our indices are stored on a single shard, being the default setting, but this can be configured when creating indices. Up until Elasticsearch version 7, the default was actually for an index to have 5 shards. However, having 5 shards for very small indices is very unnecessary. When people created lots of small indices within small clusters, they ran into an issue of over-sharding, meaning that they had way too many shards. At the same time, it was previously not possible to change the number of shards once an index had been created. So what you had to do when you needed to increase the number of shards was to create a new index with more shards and move over the documents. This was not only inconvenient, but could also be a time-consuming process. To overcome these challenges, indices are now created with a single shard by default, since Elasticsearch version 7. For small to medium-sized indices, this is likely to be sufficient. If you do need to increase the number of shards, there is a split API for this. It still involves creating a new index, but the process is much easier as Elasticsearch handles the heavy lifting for us. To go the other way, i.e. to reduce the number of shards, there is a shrink API that does this for us. These are both topics for later in the course, but for now I just want you to know that the default number of shards for an index is 1, and that this can be changed if need be. That being said, you should try to anticipate how many documents an index will contain in the not too distant future when creating an index. If you think that you will store millions of documents within an index, you might want to consider adding a few shards at index creation. Adding the additional shards at the beginning is just easier for you, and you are less likely to run into bottlenecks down the road. So how many shards should you choose then? This is a question I get asked a lot. Unfortunately, there is no correct answer to this question, other than it depends. I know that's probably not the answer you were hoping for. There is no definitive answer to this, because it depends on a number of factors, such as the number of nodes within the cluster, the capacity of the nodes, the number of indices and their sizes, the number of queries run against the indices, etc. Needless to say, there are a lot of variables involved, so there's really no formula that you can use. However, as a rule of thumb, a decent place to start would be to choose 5 shards if you anticipate millions of documents to be added to an index. Otherwise, you should be completely fine sticking to the default of 1 shard and then increase the number if need be. So to recap, sharding is a way to subdivide an index into smaller pieces, each being a shard. This serves 2 main purposes: enabling the index to grow in size and to improve the throughput of the index. The main reason is to scale data storage, so the increased throughput is probably more of a bonus. By using sharding, you can store an index taking up 700 GB of disk space, even if you have no single node that can store that amount of data. An index defaults to having 1 shard. For small to medium indices, that's usually enough. For indices that you anticipate will store lots of data, you might want to increase the number of shards at index creation. A decent number for most of these cases would be 5, but it depends on a number of factors. If in doubt, I recommend that you just go with the default values and take it from there.